Hello everyone, today's video is on Force and Pressure, Chapter 8, Class 8. Before starting this video, please like and subscribe to my channel linked in Pharma. Let's start. Introduction to Force and Pressure. Force and pressure are fundamental concepts in physics that govern the behavior of objects in our physical world. Force is a vector quantity that describes the push or pull applied to an object, causing it to accelerate, decelerate, or deform. It is responsible for creating motion and changing the state of an object's rest. Pressure, on the other hand, is the measure of force distributed over a given area. It plays a crucial role in understanding how forces are transmitted through fluids and solids, influencing various aspects of everyday life, from the flight of an airplane to the sensation of touch. This introduction provides a glimpse into the interconnected nature of force and pressure, underlying many phenomena we encounter in the world around us. Force, a push or a pull. Force is a physical quantity that represents a push or a pull applied to an object. It causes an object to accelerate, decelerate, or deform, altering its state of motion or shape. Here are a few examples of force in action. Pushing a door. When you push a door to open it, you apply a force to overcome the friction holding the door in place. The force you exert causes the door to move and eventually swing open. Pulling a cart. When you pull a cart, you are applying a force that opposes the friction between the cart's wheels and the ground. This force propels the cart forward. Gravity. The force of gravity pulls objects towards the Earth's surface. When you drop a ball, gravity accelerates it downward, and it falls due to this force. Pushing a swing. To make a swing move back and forth, you push it with force. This force imparts motion to the swing, overcoming inertia. Tension in a rope. When you pull a rope or a string from both ends, you create tension in the rope. This tension force keeps the rope taut. Magnetic force. Magnets exert a force on objects with magnetic properties. For example, when you bring a magnet close to a metal object, the magnetic force can attract or repel the object. Spring compression. Pushing or compressing a spring results in a force that tries to restore the spring to its original shape. This force is known as the spring force or elastic force. Lifting a weight. When you lift a weight, such as a dumbbell, you apply an upward force against the force of gravity. This force enables you to overcome gravity's pull and raise the weight. Kicking a soccer ball. When you kick a soccer ball, your foot applies a force to the ball, giving it motion and causing it to move in the desired direction. Wind pushing a flag. The force of the wind pushes against a flag, causing it to flap and wave. The stronger the wind, the greater the force exerted on the flag. These examples illustrate how force is involved in a wide range of everyday actions and phenomena, shaping the way objects move and interact with each other and their environment. Forces are due to an interaction. Forces arise as a result of interactions between objects or substances. These interactions can be direct, such as physical contact, or indirect, like gravitational or electromagnetic influences. Here are some examples of forces that emerge from various interactions. Contact force. When you push a book across a table, your hand exerts a contact force on the book. This force arises from the interaction between your hand and the book's surface. Frictional force. When you slide a box across the floor, the frictional force opposes the motion. This force occurs due to the interaction between the surfaces of the box and the floor. Tension force. When you pull on a rope from both ends, the tension force develops along the length of the rope. This force arises from the interaction between the individual fibers within the rope. Normal force. When you place a book on a table, the table exerts an upward normal force on the book. This force is the result of the interaction between the book and the table's surface, counteracting the force of gravity. Electromagnetic force. Magnets exert forces on each other due to their interaction through electromagnetic fields. Like charges repel, and opposite charges attract, showcasing the electromagnetic interaction. Gravity. The force that causes objects to fall towards the Earth is due to the gravitational interaction between the object and the Earth. This interaction also keeps planets in orbit around the Sun. Air resistance. When an object moves through the air resistance or drag opposes its motion. This force is a result of the interaction between the object's surface and air molecules. Spring force. Compressing or stretching a spring results in a spring force that tries to restore the spring to its equilibrium position. This force is a consequence of the interaction between the atoms or molecules within the spring. Nuclear forces. Within atomic nuclei, strong nuclear forces are responsible for binding protons and neutrons together despite their electromagnetic repulsion. This interaction is essential for the stability of matter. Magnetic force. A moving charged particle, such as an electron, creates a magnetic field that can interact with other charged particles. This interaction leads to the magnetic force. These examples demonstrate the diverse ways in which forces arise due to interactions between different entities. The study of these forces and their effects is crucial in understanding the behavior of objects and the underlying principles of physics. Exploring forces. The world around us is governed by a myriad of forces, each playing a distinct role in shaping the behavior of objects and phenomena. As we delve into the realm of forces, we uncover the fascinating interactions that underlie motion, stability, and change. Here's a journey into exploring forces. 1. Understanding force types. Forces come in various forms, such as contact forces like friction, tension, and normal forces, and non-contact forces like gravity, electromagnetic forces, and nuclear forces. Exploring these types allows us to comprehend the diverse mechanisms driving interactions. 2. Nature of interactions. Forces arise from interactions between objects, arising either due to direct contact or through fields like gravity and magnetism. Investigating the nature of these interactions unveils the invisible threads that connect the physical world. 3. Quantifying forces. Measuring forces enables us to describe and compare their effects. Units like newtons, N, help quantify the magnitude of forces, aiding in precise analysis and predictions. 4. Balancing act. In equilibrium, forces are balanced, resulting in no net motion. Exploring balanced forces reveals how objects remain at rest or maintain constant velocity, presenting a fundamental principle in physics. 5. Unleashing motion. Imbalanced forces lead to acceleration, causing objects to speed up, slow down, or change direction. Unraveling the connection between force and motion helps predict outcomes in dynamic scenarios. 6. Friction's impact. Friction, a ubiquitous force, opposes motion and affects everyday actions. By examining friction's role, we can enhance efficiency, design better systems, and reduce wear and tear. 7. Forces in equilibrium. Objects under multiple forces can achieve equilibrium when those forces balance out. Studying forces in equilibrium helps us analyze complex structures and systems. 8. Forces in nature. Natural phenomena like earthquakes, ocean tides, and planetary orbits involve intricate forces. Exploring these forces unveils the interplay between various factors and provides insights into Earth's dynamic processes. 9. Engineering and innovation. Harnessing forces has driven technological advancements. From bridges to spacecraft, understanding forces enables engineers to design robust structures and systems that withstand various conditions. 10. Limiting factors. Forces also dictate limits, like the tensile strength of materials or the maximum velocity an object can attain before air resistance becomes overwhelming. These limits shape design considerations and safety precautions. 11. Universal principles. The study of forces reveals universal principles, like Newton's laws of motion, that govern interactions across the universe. These principles extend from the microscopic scale to celestial bodies. 12. Curiosity unleashed. Exploring forces sparks curiosity, leading to questions about the fundamental nature of matter, energy, and the cosmos. This pursuit continues to inspire breakthroughs in physics and our understanding of the universe. In essence, exploring forces is a journey that unveils the intricate tapestry of interactions shaping our world. From the smallest particle to the grandest cosmic phenomena, forces are the threads that weave the fabric of reality, inviting us to unravel their mysteries and expand the boundaries of our knowledge. Forces, with their magnitude and direction, are the invisible hands molding the physical world. Understanding the differences between forces and their applications provides insights into the intricacies of motion, stability, and change. Here's an exploration into the world of forces, delving into their magnitude, differences, and applications. 1. Magnitude of forces. The magnitude of a force quantifies its strength, determining the impact it has on an object. Larger magnitudes lead to greater acceleration or deformation, while smaller magnitudes result in subtler effects. 2. Comparing forces. Understanding the differences between forces is essential in analyzing their effects. When multiple forces act on an object, their combined influence depends on both their magnitudes and directions. 3. Net force. The difference between two or more forces acting on an object determines the net force. A net force produces acceleration in the direction of the resulting force, influencing an object's motion. 4. Balancing and unbalancing. When forces are balanced, their magnitudes are equal and opposite, resulting in equilibrium. Unbalanced forces, on the other hand, lead to acceleration, either causing an object to move or changing its velocity. 5. Force in the same direction. When forces act on an object in the same direction, their magnitudes add together. For example, if you push a cart with a force of 10 N and your friend pushes it with a force of 8 N in the same direction, the total force on the cart is 18 N. 6. Force in opposite directions. If two forces act on an object in opposite directions, the difference between their magnitudes determines the net force. For instance, if you pull a box with a force of 20 N to the right and your friend pulls with a force of 15 N to the left, the net force is 5 N to the right. 7. Applications in everyday life. Forces influence various aspects of our daily experiences. From driving a car, pushing the gas pedal, to braking, applying friction against the wheels, our actions involve manipulating forces to control motion. 8. Force in sports. In sports, forces are pivotal. Throwing a ball, hitting a baseball, or kicking a soccer ball all rely on applying forces in specific ways to achieve desired outcomes. 9. Engineering marvels. Engineers harness forces to construct bridges, buildings, and machines that can withstand external pressures. By understanding the forces involved, engineers design structures with optimal strength and stability. 10. Space exploration. Even in space, forces shape trajectories and determine the motion of spacecraft. Newton's laws of motion guide space missions, ensuring precision in navigation and maneuvering. 11. Predicting natural phenomena. Forces explain natural phenomena, such as predicting the trajectory of a falling object or understanding the forces that trigger earthquakes. This knowledge aids in preparedness and mitigation. 12. Expanding frontiers. The exploration of forces continually expands our understanding of the universe. Forces at subatomic scales, gravitational interactions between galaxies, and the unification of fundamental forces challenge us to push boundaries. In the grand tapestry of the cosmos, forces are the threads weaving together motion, structure, and transformation. By appreciating the magnitude, differences, and applications of forces, we unlock the secrets of the universe's mechanisms and advance our journey of discovery. A force can change the state of motion. The term, state of motion, refers to the condition or situation in which an object finds itself with respect to its movement or lack thereof. It encompasses various aspects of an object's motion, including its speed, direction, and whether it is at rest or in motion. In essence, the state of motion provides a comprehensive description of how an object is behaving in terms of its movement or stillness within a given reference frame. In the intricate dance of the physical world, forces emerge as the choreographers of change. A fundamental truth emerges: a force possesses the power to reshape the very fabric of motion. Here's a closer look at how a force can transform an object's state of motion. 1. Initiating motion. A stationary object, devoid of motion, can be stirred into action by the application of force. When a force is applied to an object, it overcomes its initial inertia and sets it in motion. 2. Altering velocity. If an object is already in motion, a force can intervene to alter its velocity. A force applied in the direction of motion boosts speed, while a force in the opposite direction decelerates the object. 3. Speeding up and slowing down. A force can accelerate an object, causing it to speed up. Conversely, a force opposing its motion can bring an object to a halt or slow it down gradually. 4. Changing direction. Beyond mere speed changes, forces can nudge an object to change its direction. This redirection occurs when the applied force isn't aligned with the object's current trajectory. 5. Maintaining uniform motion. To keep an object moving uniformly in a straight line, a balanced force is needed to counteract opposing factors like friction or air resistance. This showcases a force's role in maintaining consistent motion. 6. Achieving equilibrium. The balance of forces on an object yields equilibrium, where there is no net force causing acceleration. This equilibrium sustains objects in a state of rest or constant velocity. 7. Complex interactions. In real-world scenarios, multiple forces often interact, shaping intricate motions. For instance, a skater's movements involve pushing, pulling, and balancing forces. 8. Gravitational influence. The force of gravity is a prime example of how a force can change motion. It pulls objects towards the Earth's surface, dictating the trajectory of falling objects. 9. Orbital mechanics. In the celestial arena, forces determine the orbits of planets, moons, and satellites. The interplay of gravitational forces between celestial bodies governs their mesmerizing dances. 10. Propelling innovation. Our mastery of forces has led to innovations like engines, turbines, and rockets. These inventions exploit forces to achieve controlled propulsion and motion. 11. Athletic achievements. In sports, forces determine an athlete's performance. From a sprinter's explosive start to a diver's precise movements, forces sculpt exceptional feats. 12. Nature's fluid dynamics. Forces govern the flow of fluids, from the currents in oceans to the winds in the atmosphere. Understanding these forces aids in weather prediction and marine navigation. In the grand narrative of existence, forces are the catalysts of transformation. With their ability to alter the course of motion, forces unravel the mysteries of motion itself, painting a portrait of our dynamic universe. Force can change the shape of an object. In the intricate interplay of forces and matter, an undeniable truth emerges: force possesses the remarkable ability to sculpt and reshape the form of an object. Here's an exploration of how force can transform the shape of an object. 1. Deformation under pressure. When force is applied to an object, especially when it's exerted uniformly over an area, the object can undergo deformation. This deformation might involve stretching, compression, or bending, altering the original shape. 2. Compressive forces. Forces that push or compress an object can cause it to shrink or become more compact. Think of how a spring compresses when you push on it, or how a cushion compresses when you sit on it. 3. Tensile forces. Forces that pull or stretch an object can lead to elongation. A classic example is the stretching of a rubber band when pulled from both ends. 4. Shear forces. Shear forces act parallel to the surface of an object, causing its layers to shift against each other. This can result in a change in shape, as seen when cutting paper with scissors. 5. Twisting and torque. Applying force in a twisting manner, known as torque, can cause an object to twist or rotate. This is how screws, nuts, and bolts work, altering an object's shape by locking components together. 6. Material properties. The response of an object to applied force depends on its material properties, such as elasticity, rigidity, and ductility. Different materials exhibit unique behaviors when subjected to force. 7. Plastic deformation. If the applied force surpasses a material's elastic limit, it can lead to permanent deformation known as plastic deformation. This can result in a new, altered shape that the material retains even after the force is removed. 8. Structural applications. Engineers and architects leverage force-induced shape changes to design structures that can bear loads, resist stress, and adapt to changing conditions. 9. Reshaping through pressure. Metalworking techniques like forging and stamping rely on force to reshape raw materials into desired forms, contributing to industries like manufacturing and construction. 10. Biological context. Even in living organisms, forces play a role in shaping and maintaining structure. Bone growth and muscle contraction are examples of how forces influence biological forms. 11. Artistic expression. Artists and sculptors manipulate materials by applying force to create intricate shapes and forms, showcasing the fusion of creativity and force-induced transformation. 12. Dynamic balance. The interplay of forces that cause deformation and those that resist it maintains a dynamic equilibrium, dictating an object's stability and structural integrity. In the grand theater of existence, forces wield the power of transformation. By reshaping objects with their touch, forces reveal the malleable nature of matter and the intricate dance between external influences and the internal structure of things. Contact forces. Contact forces are interactions that occur when two objects physically touch each other. These forces arise from direct contact and can have various effects on the objects involved. Here are a few types of contact forces. Frictional force. Friction is a contact force that opposes the relative motion or attempted motion between two surfaces in contact. It can impede motion or help maintain stability, such as when walking or driving. Normal force. The normal force is the contact force exerted by a surface that supports an object's weight. For example, when you stand on the ground exerts an upward normal force to counteract your weight. Tension force. Tension is a contact force that occurs when an object is pulled or suspended by a rope, string, or cable. It is transmitted through the length of the rope and maintains the object's equilibrium. Applied force. Applied force is a direct contact force that one object applies to another by pushing or pulling. Pushing a cart or lifting a book are examples of applied forces. Muscular forces. Muscular forces, also known as muscular contractions, are generated by the contraction and relaxation of muscles within the human body. These forces enable movement, maintain posture, and facilitate various bodily functions. Here are different types of muscular forces. Concentric contraction. In this type of muscular contraction, the muscle shortens as it generates force. It's commonly associated with movements like lifting a weight during a bicep curl. Eccentric contraction. Eccentric contraction occurs when a muscle lengthens under tension. This is often observed when slowly lowering weight during exercise. Isometric contraction. Isometric contraction involves muscle tension without significant change in muscle length. Holding a static position, like planking, involves isometric contraction. Agonist and antagonist muscles. Muscles often work in pairs, with the agonist muscle contracting to create movement and the antagonist muscle relaxing to allow the movement. For example, when you bend your arm, the bicep agonist contracts while the tricep antagonist relaxes. Skeletal support. Muscular forces are essential for maintaining posture and providing support to the skeleton. Muscles surrounding the spine and core, for instance, contribute to stability. Fine motor control. Muscular forces enable intricate movements like writing, typing, and playing musical instruments. The coordination of various muscles is crucial for these precise actions. Cardiac muscle contraction. The heart's muscular force, driven by cardiac muscle contractions, pumps blood throughout the body, maintaining circulation. Smooth muscle contractions. Muscular forces are also responsible for involuntary movements within organs, like the peristaltic contractions that move food through the digestive system. In both the realm of contact forces and muscular forces, interactions between matter are fundamental to how our world operates. Contact forces dictate the interactions between objects, while muscular forces within our bodies allow us to interact with our environment, enabling movement, stability, and physiological functions. Friction. Friction is a fundamental force that arises when two surfaces come into contact and resist each other's motion. It plays a crucial role in everyday life and has significant effects on various processes and phenomena. Here's a closer look at friction. Definition and types. Friction is the force that opposes the relative motion or attempted motion of objects in contact. There are two main types of friction. Static friction. This type of friction prevents the initial motion of objects at rest. It's the force you have to overcome to start moving a stationary object. Kinetic friction, also known as dynamic friction, this force opposes the motion of objects that are already in motion. Factors affecting friction. Friction depends on several factors. Surface roughness. Rougher surfaces tend to have higher friction due to increased contact points. Normal force. The force with which surfaces are pressed together affects friction. Greater normal force often leads to higher friction. Type of materials. Different materials have varying coefficients of friction, which determine the strength of friction between them. Importance and effects. Friction has widespread implications. Movement control. Friction allows us to control our movements, walk without slipping, and drive vehicles safely by providing traction. Energy dissipation. Friction transforms kinetic energy into heat energy, resulting in energy loss in mechanical systems. Braking and stopping. Friction is vital for braking in vehicles, as it reduces speed and eventually stops motion. Holding objects. Friction keeps objects in place, enabling us to grip and manipulate items. Writing and drawing. Friction between pencils, pens, or brushes and paper enables us to create marks. Minimizing and maximizing friction. Reducing friction. Lubricants, like oil and grease, are used to minimize friction between moving parts. Increasing friction. Treads on tires, rough surfaces on brakes, and specialized shoe soles are designed to increase friction when necessary. Overcoming friction. Aerodynamics. In transportation, streamlining designs reduce air resistance, which counteracts friction. Efficiency. Engineers strive to minimize friction in machinery and engines to improve efficiency and reduce wear and tear. 6. Limitations and challenges. Wear and tear. Friction can lead to the degradation of surfaces and materials over time. Challenges in space. Spacecraft face challenges due to the lack of friction. Special mechanisms are needed for controlled movement. Friction, while often perceived as a hindrance, is an indispensable force that shapes our interactions with the physical world. Its effects, both beneficial and limiting, influence various aspects of our lives, from transportation and technology to the way we move, work, and create. Non-contact forces. In the realm of physics, forces extend beyond the tangible touch of objects. Non-contact forces, also known as field forces, operate without direct physical contact, shaping the interactions between distant objects and governing the behavior of the universe. Here's an exploration of some prominent non-contact forces. Magnetic force. The magnetic force is a fundamental non-contact force arising from the interactions of magnets or moving charges. It manifests in attractive or repulsive actions between magnetic materials, such as iron and magnets. Notable aspects include magnetic poles. Magnets possess north and south poles that attract opposite poles and repel like poles. Electromagnetic applications. The magnetic force is harnessed in technology, from MRI machines to generators, where it's crucial for generating electricity. Electrostatic force. Electrostatic force emerges from the interactions of electric charges. It causes attractive or repulsive actions between charged objects. Key points include charge interaction. Opposite charges attract, while like charges repel, illustrating the fundamental nature of electrostatic force. Everyday applications. Everyday objects, like hair sticking to a comb after rubbing, demonstrate the effects of electrostatic force. Gravitational force. The gravitational force is a universal non-contact force that exists between all objects with mass. It's responsible for the attraction between celestial bodies and is described by Newton's law of universal gravitation. Noteworthy aspects are mass and distance impact. The force depends on the masses of the objects and the distance between them. Larger masses and closer distances result in stronger gravitational attraction. Planetary motion. The gravitational force governs the orbits of planets, moons, and satellites in the solar system. Pressure. Pressure, though not a traditional force, is a crucial concept that arises due to force distributed over an area. It's the non-contact force responsible for various phenomena, such as fluid flow, atmospheric pressure, and buoyancy. Highlights include fluid dynamics. Pressure plays a role in fluid mechanics, influencing the movement of liquids and gases in pipes, rivers, and air currents. Atmospheric pressure. Air pressure decreases with altitude, leading to various effects on weather, elevation, and human physiology. In this captivating dance of non-contact forces, the universe's intricate fabric is woven together. These forces span vast distances, shape celestial bodies, and guide our technological innovations. By delving into the domains of magnetic, electrostatic, gravitational forces, and pressure, we unveil the hidden dynamics that govern our reality and connect us to the cosmos. Pressure exerted by liquids and gases. The behavior of liquids and gases is intricately tied to the pressure they exert. Pressure in fluids, be it in the form of liquids or gases, is a fundamental concept that shapes various phenomena in our world. Let's delve into how liquids and gases exert pressure and their implications. 1. Pressure in liquids. Liquids exert pressure uniformly in all directions due to their inherent fluidity. This pressure is a consequence of the weight of the liquid column above and is described by Pascal's principle. Hydrostatic pressure. The pressure at any point in a liquid depends on the depth of the liquid column above it. Deeper columns result in higher pressures. Applications. Hydraulic systems, like car brakes and heavy machinery, utilize the transmission of pressure in liquids to amplify force and perform work. 2. Pressure in gases. Gases, composed of freely moving molecules, exert pressure through their collisions with surfaces. Gas pressure is a result of molecular motion and is described by the ideal gas law. Boyle's law. At constant temperature, the pressure of a gas is inversely proportional to its volume. This relationship is exploited in applications like scuba diving. Charles's law. At constant pressure, the volume of a gas is directly proportional to its absolute temperature. This principle is foundational in understanding gas behavior. 3. Atmospheric pressure. The air surrounding us exerts a pressure on every surface it touches. Atmospheric pressure decreases with increasing altitude. Barometric pressure. Atmospheric pressure is measured using barometers. It has significant implications on weather patterns, altitude sickness, and even cooking techniques. 4. Buoyancy and fluid dynamics. Pressure plays a pivotal role in buoyancy in fluid dynamics. Buoyant force. The pressure difference between the top and bottom of an object submerged in a fluid results in an upward force known as the buoyant force. Aerodynamics. Understanding air pressure around wings and other surfaces is crucial in aviation and design. 5. Fluid flow. The pressure gradient within a fluid determines its flow. High to low pressure leads to fluid movement. Bernoulli's principle. The principle explains the relationship between fluid pressure and velocity. It's key to understanding lift in aviation and the behavior of fluids in pipes. 6. Applications in engineering. Pressures. Impact on liquids and gases is harnessed in various engineering applications. Pressure cookers utilize increased pressure to raise the boiling point of water, leading to faster cooking. Pneumatic systems. Air pressure drives pneumatic systems that power tools, machinery, and automation. In the realm of liquids and gases, pressure weaves a complex narrative, influencing our environment, technology, and even our very existence. From the depths of oceans to the heights of the atmosphere, pressure molds our world, revealing the subtle dance of molecules and their effects on the physical universe. Atmospheric pressure. High above the Earth's surface, an invisible embrace envelopes us, the atmospheric pressure. This omnipresent force, exerted by the weight of the air column above us, shapes our environment and influences numerous natural and man-made processes. Let's delve into the intricacies of atmospheric pressure. 1. Definition and magnitude. Atmospheric pressure is the force per unit area exerted by the Earth's atmosphere on any surface within it. At sea level, the standard atmospheric pressure is around 101.3 kilopascals, kPa, or 14.7 pounds per square inch, psi. 2. Barometric measurements. Atmospheric pressure is commonly measured using barometers. Changes in atmospheric pressure are indicative of weather patterns. Rising pressure often signals fair weather in clearing skies. Falling pressure can indicate the approach of storms or unsettled weather. 3. Altitude dependency. As altitude increases, atmospheric pressure decreases due to the reduced weight of the air column above. This is why atmospheric pressure is lower at higher altitudes, such as on mountain peaks or in aircraft at cruising altitudes. 4. Pressure gradients. Pressure differences drive the movement of air masses, leading to wind patterns. High pressure areas, air moves from areas of high pressure to low pressure, creating winds and influencing weather systems. Low pressure areas, often associated with stormy and cloudy conditions. 5. Human effects. Our bodies are accustomed to atmospheric pressure at sea level. Changes in pressure, such as during air travel or scuba diving, can have physiological effects. Decompression sickness. Rapid pressure changes can lead to nitrogen bubbles forming in the bloodstream when diving, causing the bends. Ear and sinus discomfort. Pressure changes during flights can cause discomfort due to air trapped in body cavities. 6. Aviation and weather forecasting. Atmospheric pressure plays a crucial role in aviation and weather prediction. Aircraft instruments, altitude and airspeed indicators rely on atmospheric pressure to provide accurate readings. Weather forecasting. Changes in atmospheric pressure are used to predict weather patterns, including approaching storms and shifts in air masses. 7. Buoyancy in flight. Atmospheric pressure, along with buoyant forces, contributes to the principles of flight for birds, airplanes, and other flying objects. 8. Vacuum of space. Beyond our atmosphere, the vacuum of space results in negligible atmospheric pressure. Spacecraft must be designed to withstand this extreme pressure difference. From the ever-present weight of the atmosphere on our shoulders to the subtle influence it wields over weather, travel, and even our own bodies, atmospheric pressure is a silent force shaping the dynamic interplay of Earth's systems. It's a reminder of the intricate balance that governs our planet's processes and influences our daily experiences. Thank you for watching. Please like, share and subscribe.